So in this video, I will be implementing a very simple traffic light module in three different encoding styles. And those are binary, gray code encoding, and one hot code encoding. So let's begin. So first, I will add new file to this project. I will name it tlight, and it should be of SV type. So I will name my module tlight or traffic light, and it will have three outputs that are the green light, the yellow light, and the red light, and 5 inputs. Those are the sensor, the decrement counter for the yellow light, the decrement counter for the green light, and the active low reset. Now I will mention the direction and data type of each signals. First I will mention the outputs, which are the lights, and each of them are of single bit. Now I will mention the single bit input, which are the sensor, the clock, and the reset. First I will fix the typo here and check whether I have made any other typo. Okay, it's fine. Now I will mention the other inputs. They will be of 5 bits, or I think I should use 4 bits instead. And those are the decrement counter for the green light and the decrement counter for the Y light. Now I will mention enum logic. I will declare a type for the enum logic, and it will be used for both the present state and the next state. And each state will be of 2 bits. So my first state will be red, and I will give it the value of 0. And my second state will be green, and I will give it the value of 1. And my third state will be yellow, and I will give it the value of, okay, it should be 2. The value of 2. And I will name this type state. Next, I will declare the present state and the next state using this state data type. So first I will go ahead and check for any compilation errors, whether I have made any typos. Okay, I did made a. So I forgot to mention the data type for the counters. It should be logic, and now it should be fine. Okay, so I forgot to mention the clock signal. It's fine now. So I will go ahead and begin with my sequential logic. I will use always FF. Should be equals to red, else it should be equals to next state. So I will check for any compilation error for one more time. Okay, it's fine. Now I will begin with my combination logic, in which I will also merge the output logic. I will use always com here. I will label this as combinational as well as output logic. And I will end it. Now I will mention the default value for the states. So uh, for the next state, if the any condition does not trigger or the state does not move, then the next state should be equals to the present state. And I will also mention the default value for all the outputs. So by default, all the lights light green and the light yellow should be equals to 0. So these are the default values. So let's begin with our case statement. I will use unique case here, which is the mixture of parallel case and full case. So my case selection expression will be present state, and I will also end the case. So I will begin with my case selection items, and my case selection items for the binary design will be the states. So I will just mention the first state. So before proceeding to that, I would like to mention that right now I'm using the binary coding style because it is just incrementing one by one, because the first state holds the value of 0 and the second state holds the value of 1 and the third state holds the value of 2. So binary uses register but suffers from glitches due to more complex combination logic because multiple bits are changing at the same time. Here you can see when we will transition from the green state to the yellow state, both the bits will be changing. So this results in more complex combination logic when when the design is passed uh, with the synthesis tool. Because of the complex combination logic, there would be more switching time. And as for binary, since there are 2 bits, so the number of flip-flops will be 2. Because there could be 4 possible values, but here we are using 3 states. So for these 3 states, there will be 2 register use. So let's begin. So in the red state, so if the state is red, it will first check the value of the sensor. So if the value of the sensor equals to 1, then it will change the next state. Then it will transition to the green state. And on the same time, I will just copy it. So in the red state, of course, the red light should be high. So this is the condition for the red state. Now we will begin with the other case selection item that should be the green state. So if this is the case, then it will check the decrement counter of the green light, which is light G. So if and only it is not light G, it is count G. So if count G equals to 0, then only it will move to the next state, which will be yellow. And also here the green light should be high. So I will move with our final case selection item, which will be the yellow state. So just give me a second. So if the state is yellow, it will check whether the counter, the Y counter is equals to 0 or not, similar to the green state. So when it is 0, it will move to the next state, which will be red for this case. And of course, in this state, the yellow light should be high. So this concludes our FSM design using the binary coding, and these are the default values for the combination logic. So first, let's go ahead and check for any possible typo or any compilation error. Okay, there are 2 errors. Okay, first, this one is obvious. Let's find out. Right. Okay. Okay, so I made a mistake here in the label. Should be combinational. Okay, now it's fine. So let's go ahead and write a test bench for our design. I will also include the file, the duty file. So I will go ahead and mention all the signals. First is the green light, then it is the yellow light, then it is the red light, then it's the sensor, clock, and the reset signal. Then I will go ahead and mention our other signals, which will be of 4-bit. Those are the counter for G and the counter for Y, which is yellow. Now I will go ahead and instantiate my DUT. I will do the wildcard port declaration. Okay. Now I will go ahead and mention the toggle initial block for the core clock signal. So our clock will be low. Then forever, after every 5 time instance, let's toggle the clock. Okay. Fine. Now I will declare another initial block that will monitor literally everything. So first it will monitor, let's begin with the identifiers. First it will mention the time. Then it will mention every light. First one should be red light. And the second one should be green light. Then the third one should be yellow light. Then it should mention the values of counter. After that, finally, it should mention the present state and the next state. Let's check for any typo. Okay, there are two errors. Okay, it is fine. So let's go ahead and declare another initial block in which we will apply stimulus to the duty. So first I will check the active low reset by deasserting it. And I will repeat this for 4 times during the nagage of the clock. Now I will assert the reset signal. After that, I will give some value to each of the counters. For this example, I am giving 10 to each of the counters. So let's give it. Similarly, to the yellow counter, I will give the same value. And also, I will assert the sensor signal. So after doing that, what I will do, I wanted to transition from green state to yellow, then yellow state to the red state. And to do that, we want to make it sure that the values of the counter should be 0. So what I will do, I will repeat the values, the change in the values in each of the counter at every nagage of the clock by decrementing them. So I will just go ahead and I will use the repeat keyword. Oops. And I will repeat that for 10 times since the value of the counters are 10. And I will do that at the negative edge of each clock. First I will do that for the green counter because first we will be transitioning from red state to the green state. I will use the post decrement operator. Then I will do the same thing for the yellow counter. And after that, at the next nagage of clock, I will stop the simulation. So first, I will go ahead and check for any possible compilation error from my side. Okay, there is an error. Okay, I forgot to mention the clock here. No, it should work just fine. Yep. So this concludes our test bench for this design. So let's go ahead and simulate the code. So at the time 0, the reset was deasserted. So that's why the red signal was high as per our duty, and each of the other lights were 0. And the value of the counter was unknown because it is the default value of any logic data type. And this was our present state, and also our next state was also red because we have mentioned the default condition right here in this combination logic. So after that, we asserted the reset signal, which is active low, and we assign some value to both the counters, and we also asserted the sensor signal. So you can see the change right here. And then at every clock edge, we begin decrementing the counters one by one. So here after the okay, so I haven't mentioned any monitor input monitor signal for the sensor signal, but here you can see that our green light is asserted and our present state was green. So after that, we start decrementing the counter from 10 to 0. So you can see it right here that counter begins decrementing and our state is still green. And when only the counter becomes 0, the state transitions from green to yellow, and the yellow light asserted whereas the other lights deasserted. And the same thing happens for the yellow state, that the counter begins decrementing, and you can see it right here. And after when the counter decrements to 0, it transitions from yellow state to red state, and the red light asserts again. So this concludes the design and the test bench of our traffic light module. So let's go ahead and use the different encoding style. So for the second time, I will be using the gray code encoding, which minimizes switching because only one bit changes during the state transition from one state to another state. Thus, it minimizes the combination logic, and it also reduces the glitch and the power. So I can make a very simple modification just by changing my yellow state to 1 1. So in this way, if you will observe, each state transition when each state transitions, only one of the bit changes. For example, in the red state, the value is 0 0, and in the green state, the value is 0 1. So here only the second bit is changing from 0 to 1. And when green state transition to yellow state, the value becomes 1 1. So here also only one of the bit, which is the first bit, is transitioning from 0 to 1. So using this way, it just decreases the combination logic, and also there is a less chance of getting glitch during the simulation. So this was the Greek code encoding, and it will perform similarly to the binary encoding in this case because our FSM is not that complex, but still it takes into effect when we consider the synthesis. So let's move on to our last encoding state, which is one hot code, and it uses numbers of register equals to states, thus simplifying the logic for faster FSM, but costing more area and power. So in the one hot code encoding, each state will have its own flip-flop or register. So what it will do, it will just reduce the combination logic even more. So the switching between one state to another state becomes way faster, but still the area becomes more. So if you have resources and your priority is speed, then you should use the one hot code encoding. So to do that, I will change the size of this SSM to 3 bits, and here at a given time only one of the bits should be high. So for the red state, the third bit will be high. The green state, the second bit will be high. And for the yellow state, the first bit or the MSB bit will be high. So usually we use the reverse case statement with the one hot code encoding, and I have already demonstrated that in my previous video how to use the reverse case statement. So I will go ahead and make some minor modifications. So first I will declare another enum logic data type, which will be of 2 bits, and I will mention the bit for each of the lights. So first one should be the R bit, which will hold the value of 0, and the second one will be green bit, which will hold the value of 1, and the final one will be the yellow bit, which will hold the value of 2. And I will also change this enum logic. So if the state is red, first let's change this to 3. So if the state is red, it will shift by 1, by 0. So the value of the R bit is 0, so it will not cause any shift. So, and if the state is green, it will shift by 1, which is the value of the G bit. And if the state is yellow, it will shift by 2, which is the value of Y bit. So I also need to change the regular case statement to the reverse case statement, and I can do that just by changing the case expression to be a literal value 1. And also I need to make sure some necessary changes to be done here. So as the case selection items, I will select the present state, and as per the bits of the present state, that particular case selection item will be selected. So for this, this should be the cases and the conditions and the output for the red state. So I am assigning the LSB of the present state to the red light. So I will just mention R bit. So this particular enum has multiple usages, and it is getting used right here in this enum logic as well as in the case selection items. So if the least significant bit of the case of the present state is high, this state will be selected. Similarly, if the second bit is high, then this case will be selected, and if the MSB is high, then this case selection item will be selected. So what is happening right here is that we are using the reverse case statement, and here you can see that the present state and as well as the next state both are of state data type, and the state data type, in the state data type the labels are designed using the one hot code encoding, so only a single bit is asserted for a state. So first let's go ahead and check for any compilation error. Okay, there is one error. Okay, it's right here. I should have mentioned the name of this enum data type, state bit. No, it's fine. Now let's go ahead and check whether our test bench work for this design or not. Okay, so the design is working just fine. So that concludes our design video for the traffic light, a very simple module, and I have designed that module using the binary coding, the gray coding, and the one hot code coding. So it is better to use gray code and one hot code instead of binary code. And amongst those two, if there are some resources constraint, then you should select gray code. Otherwise, speed is the major priority, then we should select one hot code. Thank you so much.